So in this video, we're going to look at a few different methods to do some dihydroxylation reactions. Those are going to be reactions that are going to add two alcohols. In our last set of videos, we found a variety of ways to add both an alcohol and a OH. Here, we're going to look at a variety of ways to add two OH groups. And because of the fact that we're going to be adding the exact same group, an OH and an OH, there's going to be two possible ways which we can do that. One being an anti-addition, meaning they're going to have opposite stereochemistry, and the other being a same. One of the easier ways to add a set of alcohols onto a structure that are going to have anti or the opposite is going to be with opening an epoxide. And an epoxide is going to be a ring structure that's going to have three bonds. We have a structure there right in the middle. So a three-membered ring that's going to have an oxygen heteroatom. That's known as an epoxide. And opening an epoxide under acidic conditions is going to give us two alcohols that are going to be on the opposite side or anti. We're going to talk about two different methods to make epoxides in just a second. Now, if you take an epoxide and you react that in acidic conditions, what's going to happen is the oxygen on the epoxide, and maybe we'll actually draw that over here. So if you have an oxygen in your epoxide, if you expose that to an acid, that will be protonated. And we've kind of seen a variety of reactions that are kind of similar to that. And that's kind of like an oxonium-like intermediate. When you have this, that's going to be a lot more unstable and is more likely to be opened. And that's going to be opened by water. So this is going to come with a backside attack. Exact same kind of thought process between like our opening of like our bromonium or our like mercury complex structure that we showed in the last set. And when we open that, we are going to have our different groups that are going to be added. Here you're going to have scroll over just a little bit, protonated water, and then that's way too many bonds. I drew a Texas carbon. And then your alcohol. And then what you do is you do one more acid-base step where you'd have some more water. I'm just actually going to show just from this one here. Kind of quick. That would come over and then give you your product. So that's going to be opening of an epoxide. Opening of epoxides are going to give anti-addition. So those are going to be on the opposite side. If you had a product and you had a structure like this, and you went to, actually it's misleading. If you got a product and you had your two OHs, you would add one as a wedge and then the other as a dash, and they're going to be on the opposite sides. And those are going to be opening an epoxide, which is going to be just like opening a bromonium. So there are going to be two different ways in which we're going to talk about making epoxides. And you can create those either from a halohydrin. Halohydrins are going to be structures that we're going to talk about in the very next video how to make. The key kind of feature of halohydrins are they're going to be an alcohol, so an OH, and then a halogen like a bromine. You can do an epoxidation from a halohydrin. That mechanism is going to be kind of based a lot like an SN2-like structure. So if you use a basic condition, so if you use a base, that alcohol will be deprotonated and generate a structure where you have a halogen, and then you'll have your O-. That can then do a backside attack and then kick out your leaving group, and that will generate your epoxide. In our next video, we'll talk about ways to make an epoxide. We'll talk about ways to make a halohydrin. However, once you have a halohydrin, if you expose this to a base, that can form an epoxide. when you have an epoxide, if you expose that to acid, that can open up into two alcohols that are going to be on the opposite side. Now, going to make a halohydrin is actually going to take a few steps. You can do that from a double bond, and we'll learn that in our next video. One other way that you can use, though, is you can do an epoxide directly from a double bond. You don't have to always go through a halohydrin. And a common example of this is going to be with a peroxy acid. So here I've shown the structure. Well, I haven't actually shown the full structure, but MCPBA is a pretty common structure that we're going to see. The structure of MCPBA is going to be a meta chloro benzoic acid. So for this R, that R is going to equal to a benzene ring, and then there's going to be a chlorine, and then you're going to have like your peroxide stuff. So that's the actual structure of your MCPBA. We'll just write out that name most of the time. You don't need to actually draw out that full structure all the time. This is going to form a really interesting complex with our double bond and give a syn addition. Mechanistically, this is kind of complex, and I'm not going to ask you to actually reproduce this mechanism, but I'll go ahead and show it to you where you've at least seen it once. Mostly because it's going to be there's going to be some similarities with our next reaction scheme that we're going to talk about. So in your structure here, one of our kind of key mechanism steps is going to be the docking on the same side of our peroxide with our double bond. So mechanistically, this double bond is going to attack our peroxide. These electrons are going to come over here. These are going to hop over here, and then this is going to hop down here. And that's a lot of electrons moving. That's one of the reasons why I don't need you to see that entire or be able to like draw that all from memory or anything. This is going to form an obnoxious looking transition state. And these dotted bonds are bonds that are either being broken or being formed. And then so we have the carbon and the oxygen. And then like your R group. So this right here is your transition state. Even though all those arrows look super crazy, it's actually just going to be this 5-membered ring and the 3-membered ring, the epoxide, and you're just going to be kind of dancing electrons around. And what that's going to generate is an epoxide. Your epoxides need to be a syn addition because the torsion of trying to put it on the opposite sides, it's impossible. You can't make a triangle. But it'll be a syn addition. And it will also then generate the product of the MCPBA is just going to be just a carboxylic acid rather than the peroxide. So you'll have just your OH and then like your R. So this just generates a carboxylic acid, which you can separate. So 2 different ways in which you can make epoxides. The first is going to be from a peroxy acid. Those are going to be like a structure like our MCPBA. That's going to stand for our metachloro peroxybenzoic acid. Mechanistically, there's a bunch of stuff that goes on, but it makes an epoxide, and that's the kind of key takeaway. Secondly, if you have a halohydrin, which we'll learn how to make in our next video, you can expose that to a base. When you expose that to a base, your alcohol gets deprotonated, and then it's going to attack your leaving group in kind of like an SN2 fashion. So attack and then leave. That's going to create an epoxide. Once you make an epoxide, epoxides are really good handles to do some chemistry. One of the nicest things you can do with them is just expose them to acid. And if you expose it to acid, you're going to protonate that epoxide, and then that can be opened up in an anti form to add your OH on your opposite sides. So there's 2 different ways to make epoxides, and when you generate that epoxide, you can generate a di-alcohol species that is anti-addition. Now, you can also do some chemistry to add 2 alcohols, but on the same side rather than the opposite side. and that's going to be what we talk about in a second. So there are going to be two reaction conditions which we're going to learn in order to do a syn addition. So that's going to be addition to the same side of a double bond with two alcohols. So this would be a syn addition of two alcohols. These are going to be using either a osmium tetraoxide, so OSO4, or using a permanganate, a KMNO4. KMNO4 is actually really reactive, and in our next video, we're going to see another reaction with it where it's actually going to break bonds. So if we do use permanganate, we actually need to do this in very cold conditions to avoid unwanted byproducts. So the mechanism for both of these are actually going to be very similar, and the kind of key differences between these when we're kind of thinking about either the osmium or the KMNO4. For our osmium, the osmium gives really, really good yields. So this gives great yields. However, it is hella expensive. Osmium is not an easy chemical to come by, and you need a mole equivalent of it in order to do these reactions. And because of that, you have to spend a ton of money to do that reaction. KMNO4 is the cheap version. However, because of the fact that it's cheap, its yields are pretty low. So low yields. It also can give some unwanted byproducts, and we'll talk about those byproducts in the next video when we're talking about number 12, which is our ozonolysis. Or maybe a positive, it is cheap. So depending on how valuable your starting material is, if it's a pretty cheap starting material, then you just use KMNO4. It's cheap. If you get some byproducts, that's fine. If you lose some stuff, that's fine. If you have a super valuable starting material, you might use the osmium so you don't lose out on some of your precious material and you just suffer the cost. Now, for both of these, the osmium or the permanganate, you're going to form a 5-membered ring that's going to have your syn addition of your two alcohols. We're just going to draw just a little bit of this kind of mechanism. We're not going to draw all of it. So we'll have a double bond, and you'll have a structure like your osmium tetraoxide. Similarly, if you do the KMNO4, it's almost the exact same. You'll have a manganese that has a bunch of double bonds. One of them, though, will just be a single bond, and that's where your potassium comes in. But the general structure is the same on the attacking side. What's going to happen is you're going to get a total of 3 reaction arrows to make a 5-membered ring. So you're going to have a new bond that's going to be from here. This is going to come over here, and then this is going to come over there. So there's going to be a total of 3 sets of reaction arrows that are going to cyclize, kind of similar to some of the ones that we showed before. You don't need to be able to reproduce this. Overall, you're going to form a intermediate that is going to look like this, and I guess you have a lone pair. And then what you're going to do is you're going to, in the second step, you're going to use, for example, your peroxide or your base, and that's going to hydrolyze, and those hydrolyze is going to cut that off right there. So hydrolyze. How do you spell hydrolyze? That's just now. So that's going to hydrolyze and give us your two OHs, and you'll see that these are going to be on the same side because that osmium or that permanganate connected. Where on our other ones, like our epoxide, we did a backside attack. So ultimately, there are a handful of ways in which we can make epoxides and add two OHs. When we're thinking of our epoxides, we can either use a peroxy acid, or we can use base and a halohydrin. If you have an epoxide, you can get an anti-addition of two alcohols under acidic conditions, or you can either use osmium or permanganate to get a syn addition of your two alcohols. And those are kind of our key ways to kind of make some key epoxides and some dihydroxylation reactions.